let's review for the Unit 8 exam on rotation. And what I want to do is give you kind of just a list of the ideas without a lot of lecturing about them, just kind of reviewing everything that we've done. And then I'll give you a little bit of a play-by-play on the kind of problems I'm going to give you. I haven't actually written the test yet, but I'll do the best I can to give you an accurate list of the problems that will be on the test. Okay, so we're dealing with objects that rotate, and so the first thing we're going to do is have a rotational kinematics. Now, kinematics is the description of motion. So if I've got an object that's going to rotate, and here I'll just draw like a little disc shape thing that's going to be rotated around. And I will zoom in a little bit, but when I go off screen, let me know. So first thing we need to do is if we rotate this thing around, let's say you're like a little ant on this disk that's rotating around, you're going to go through some arc length. And we're going to call that delta S. That's from here wrapped around here. That's how far I went, what distance I traveled as I went around this circle. Okay, and this thing is spinning around some axis. And we call this delta theta right in here. That's delta theta. And then this has some radius r. And our object doesn't have to be all the way on the outside edge. It can be halfway in between. The arc can be smaller than the maximum radius of the object. But this is the arc length that object traveled through. And that arc length is equal to r times the change in angle. Now remember, this is how we defined an angle. You know, delta theta equals the arc length divided by the radius. The arc length divided by the radius, that will give us a ratio of a length over a length. But really what that's defined to be is how many radians you've gone through. If you take one radius and wrap it around the outside here, the angle that is swept out is called 1 radian. That's the definition of a radian. So this delta theta has to be in radians. If we take both sides and divide it by time, we get speed. So the speed of this object out here is equal to the radius of, now delta theta over delta t, we call that angular velocity. So the linear velocity, the speed, is going to be r times omega. Now, if I'm accelerating this thing, that is, if there is a tangential acceleration of our object on here, that is, the speed is getting faster and faster and faster, well, the speed is equal to, the tangential acceleration is equal to r times alpha, and alpha is the angular acceleration in radians per second squared. And of course, the change in angular velocity over the change in time is equal to the angular acceleration. So these are how the linear, the displacements, and the tangential acceleration are described in terms of the angular motion variables. Now, the centripetal, or now we call it the radial acceleration, is equal to v squared over r, but v is equal to r omega. So we square that, r squared omega squared over r gives us r omega squared. And this is the centripetal acceleration. Remember, a sub t, this acceleration, this is the rate at which you're changing your speed going around that disk. But this is your radial acceleration, that's the centripetal acceleration. That's the thing that's keeping, that's the rate at which we're changing the direction of it. Okay. Now, remember that you have different ways of measuring angles. You have revolutions. If you have one revolution, you've gone through, or one rotation. Sometimes they're called rotations. And in what we're going to study later today, we call them cycles or whatever. But a revolution is 360 degrees, isn't it? But 360 degrees is 2 pi radians. So these are the conversion factors you need, okay, to go. Now, in these expressions here, both delta theta, omega, and alpha must be in terms of radians. If they're not, then your answer is going to be all screwy. And that's because r is in terms of radian. R is like meters per radian. R, the radial distance here, is really the number of meters you go through delta S to get, 1 radian. If you take the radius and wrap it around the outside, you've gone through 1 radian. Okay. Well, we also defined the period. The time it takes to go around once is equal to 1 over the frequency. The frequency, that's 1 over the period. Also, and I wrote this down wrong. I made a mistake earlier in the like 2 weeks ago. But the frequency, that's in hertz. That's in revolutions per second. That's equal to the angular velocity in radians per second divided by 2 pi radians per revolution. So this is the conversion factor, which means that the period is equal to 2 pi divided by omega. So these are just little equations between frequency, angular frequency, period, and their relationships. Okay, then we got into dynamics, rotational dynamics. And, what causes objects to angularly accelerate? Well, I'm sorry. You know what? I could fit it over here. I could fit it over here instead. Before we get to rotational, we have the kinematic equations. Where the angular acceleration is a constant. This is all still under rotational kinematics. Well, we had omega equals omega naught plus angular acceleration times time. This is if the angular acceleration is a constant. And then we had delta theta equals the average angular velocity times time. Then we had the change in angle is equal to the initial angular velocity times time plus 1/2 the angular acceleration times time squared. And then the final angular velocity squared is equal to the initial angular velocity squared plus twice the angular acceleration times the change in angle. And these are the kinematic equations for rotational motion, and they only work when the angular acceleration is a constant. Okay, well, in rotational kinematics, or rotational dynamics, I should say, well, look, we had net force, right? Equals mass times acceleration. Well, this was translational dynamics, or linear dynamics. Now we're going to have the net torque is equal to I alpha. Now this was the sum. Oh, that was terrible. The sum of all the forces acting on our object. This is going to be the sum of all torques. acting on it. See how dynamics is basically the same thing. The net force, the net torque. And instead of mass, we have, which is another way of saying mass is inertia. Well, this is rotational inertia. Okay. Well, what is a torque? A torque is well, it's R times F times sine theta. It's a force, but it's only the force that's perpendicular to R, or your radius, or your, the from the axis of rotation to the application of the force. For example, if I have a stick and I pin it down, or right here, so that it has to rotate around this axis, and then I just apply some force to it, like this, F. Well, here's your R. R is from the axis of rotation to the application of the force, and then if you extend R out like that, it makes it an angle theta, like this. Only the component of the force here that's perpendicular to R is contributing any torque, any twisting kind of force. So this F sine theta, that's what this part is right here. Now, F cosine theta, that is the component of the force that's along our lever arm R. Well, that doesn't apply any torque, it just pulls on it. But you have it pinned down here, so that force isn't going to do anything. It's going to get canceled out. But the perpendicular component of that force, that causes a twisting force. Now, if you're trying to make it twist this way, then that's a positive torque. If you have another force on it that's going like this, then that's going to be a negative torque. But if you add the two torques together, you'll get the net torque. Now, in order to figure out what the net torque is, how much angular acceleration you get, you need to know rotational inertia. Now, rotational inertia is defined for, if you have particles, if you have one particle, it's mr squared. If you have multiple particles, it's the sum of each particle, and it's r squared. And if you have an extended object, let's say you've got a disc or a bowling ball or a hoop or something like that, it's going to be some fraction of mr squared. Or if you have a stick, it's going to be some fraction of the object's mass times its length squared. I will give this to you. This one I will give to you. But I might give you an object with made out of two particles. And you have to figure out the rotational inertia of that. Well, it's just mr squared for one plus mr squared for the other. And notice that rotational inertia has units of kilograms times meter squared. So rotational inertia, it's not just how much stuff you have, but where that stuff is compared to your axis of rotation. Okay. Now, what if you have, let's think of it in terms of energy. Well, I have kinetic energy, K equals 1/2 mv squared. Well, we have the rotational equivalent of that, and we derive this 1/2 the rotational inertia times omega squared. Now, of course, if I have some object that's rolling, like a wheel, and it's moving like this, but it's also rolling, well, now this rolling object has both kinetic energy, linear kinetic energy, and rotational kinetic energy. And V is equal to R omega. So when you add them together, the the total kinetic energy is equal to 1/2 mv squared plus 1/2 I omega squared. Now remember, if it's rolling motion, you can substitute, well, omega equals v over r, so this would be v over r quantity squared. And if I is a function of the mass and r squared, the r squareds can cancel. You can just add these together into one term. But I will give you a problem where you have a rolling object and you have to figure out how much kinetic energy it has in a linear sense and in a rotational sense as well. And then the total. And then finally, and unfortunately I didn't get this all onto one page, we have angular momentum. And I guess, let's zoom out. And I already wrote this up. Look, we have linear momentum where we have, P equals m times v. Well, if we just multiply, these times r, this r here, r times p becomes L, and r times m becomes I, and you have the v becomes omega. So you've got we have this definition for angular momentum. L equals I times omega. Now, if you have a net force of 0, then your linear momentum is conserved. But if you have a net torque that's equal to 0, well, then your angular momentum is conserved. So the rotational inertia times the angular velocity equals the rotational inertia times the angular velocity. And I'll probably give you a skater type problem. A figure skater goes into a spin. They pull their arms in. By pulling their arms in, they decrease their rotational inertia. But since momentum is conserved, since there's no net torque on that skater, then you can solve for the final angular velocity of the skater. Or if you know the final angular velocity, I'll give you 3 out of 4 of these, and then you have to figure out what the other one is. But you have to recognize when you can say that the angular momentum is conserved. Because look, I might give you a problem where there is a net torque, and if there might be multiple torques. You have to figure out what the net torque is, and that net torque is equal to I alpha. So now here we have, let me zoom all the way out. Let's see if I get all of this. Now this gives you a map on the kind of problems I'm going to give. I'm going to give a problem where, I'm going to see if you understand the relationship between the arc length, the change in angle, the speed, the angular velocity, all of this stuff. I'm going to see if you can convert from revolutions to radians to degrees. I'm going to give you a situation where the angular acceleration is constant. Can you use the kinematic equations? Then I'll give you some object that will have more than one torque on it, and you'll have to figure out what, you have to add up those torques and then figure out what the angular acceleration is. I'll give you the rotational inertia, or you'll have to solve for it. I'll give you like a rolling motion object and probably ask you to figure out what is the speed. Maybe I'll give you omega and you have to figure out the speed. And once you know the speed, you can figure out the linear and rotational kinetic energies. So there'll be an energy problem and a rolling motion problem. And then I'm definitely going to give you an angular momentum problem. Under what circumstances is angular momentum conserved? Well, that's when the net torque is equal to 0. So under what circumstances is angular momentum changing? Well, that's when a net torque. If you have a net torque, really, if you have a net torque, well, that's the rate at which angular momentum changes. Just as the net force, am I still on screen? Nope. Just as a net force is really the rate at which momentum changes, linear momentum. So one thing you can see by looking at all of this, let's see if I can get it all on there now, is that everything that we've done in this unit, where the description of motion, constant acceleration, dynamics, energy, and momentum. And this is just a repeat of everything we did before, but now for objects that rotate instead of objects that translate. So if you forget an equation, you can always think, okay, what's the equivalent in rotational? What's the equivalent in translational motion or kinematics or dynamics or whatever, and just translate it to rotational variables, and you'll be right. Any questions? Okay. That is all.